This video explores the physics of artificial muscles, specifically dielectric elastomer actuators, DEAs, showing how soft stretchable capacitors convert electric fields into powerful, rubber-like motion. The core principle involves electrostatic compression, where voltage generates an electric field, creating Maxwell stress that squeezes the elastomer and causes lateral expansion. A DEA consists of a soft dielectric elastomer situated between two stretchable electrodes. The elastomer acts as an insulator and deforms mechanically. It is crucial to note that the elastomer moves due to field-induced stress, not because electricity flows through it like a wire. The actuation of a DEA is a chain reaction. It begins with the applied voltage generating an electric field, which creates electrostatic pressure. This pressure leads to thickness compression, ultimately resulting in area expansion. The electrical driver follows the capacitor model. Electric field East equals voltage V divided by film thickness T. Minimizing thickness is critical because a smaller thickness produces a much larger electric field for the same applied voltage. The force is defined by Maxwell's stress, where pressure scales with the square of the voltage and is inversely proportional to the square of the thickness. Thinner films exponentially increase actuation strength without increasing voltage, and reversing polarity does not reverse actuation. The physical response of rubber-like elastomers is near incompressibility, meaning volume remains constant. When the electric field compresses the thickness, the area must expand in plane. Actuation is a mechanical balance between electric pressure and the elastomer's stiffness, or Young's modulus. To maximize actuation, increase voltage or polarizability, and decrease thickness or stiffness. The 7-step actuation cycle starts with no voltage, followed by applying voltage, which forms a field. Charges attract, creating Maxwell pressure, which drops thickness. Area expands, and coupling changes capacitance, completing the cycle. A numerical example with a 50 micrometer film and 3000 V applied voltage results in a strong electric field, Maxwell pressure comparable to atmospheric pressure, and nearly a 10% reduction in film thickness. Two lenses explain DEA function: the mechanical force framework, based on Maxwell pressure, and the thermodynamic energy framework, based on maximizing energy storage by increasing capacitance. Both views describe the same qualitative mechanism. Mechanical pre-stretch is an engineering hack used to thin the film, increase the electric field, suppress wrinkling, improve stability, and alter stiffness. This allows for larger, stable deformations. A major limitation is electromechanical instability, or pull-in instability. This is a runaway feedback loop where the film getting thinner increases the electric field and Maxwell pressure, which makes the film even thinner, causing collapse. Failure mechanisms include dielectric breakdown from an excessive E field, electromechanical instability causing collapse, mechanical rupture from overstretching, viscoelastic creep from sustained load, and electrode failure due to stretching damage. Dispelling common myths: the elastomer is an insulator, sideways expansion is a byproduct of incompressibility, pressure depends on the square of the E field, and higher voltage increases the risk of breakdown and instability. In summary, voltage initiates the electric field, which generates mechanical pressure. This pressure dictates vertical strain, and volume preservation forces dramatic sideways expansion. A dielectric elastomer turns electric field pressure into large, rubber-like motion. This flowchart details the governing physics engine for DEAs. Applied voltage creates an electric field, which can lead to Maxwell pressure or electrical breakdown. Maxwell pressure causes thickness compression, which in turn leads to expansion and motion. Mechanical energy density scales with the fourth power of the electric field. Breakdown strength is critical, as modest gains in the safe field produce disproportionately large gains in useful work density. The pull-in loop illustrates the instability risk. Material choice presents sharp trade-offs. Acrylic offers extreme stretch but high loss. Silicone allows fast dynamics but has lower permittivity. Polyurethane has high permittivity but is much stiffer. High modified materials balance high permittivity with low modulus. Pushing planar strain is the chemistry frontier. PFED-10 delivered significant area strain under biaxial pre-stretch and maintained good reliability and bandwidth, showing strong performance compared to other materials. The compliant electrode ecosystem includes carbon-based, liquid metal, hydrogel and ionogel, and thin metal films. Each option offers specific pros and cons regarding conductivity, compliance, processability, and fabrication complexity. Electrical breakdown often occurs at the weakest interface or defect in a dielectric elastomer actuator, not at the ideal material limit. Carbon black electrodes can reduce the median breakdown field by about 30 to 40% on thin silicone. Optimization of dielectric elastomer actuators requires a multi-dimensional approach. Focusing only on a single metric, such as higher permittivity, can degrade other important characteristics like breakdown strength and low modulus. System-level optimization is the true frontier. DEA architectures act as motion transformers. Examples include planar membranes for in-plane expansion, rolled actuators for axial contraction, cone/diaphragms for radial displacement, and stacked high-force structures for linear contraction. DEAs enable high-impact locomotion and robotics. Benchmarks show speeds up to 20.6 body lengths per second and forces up to 30 newtons, enabling a 45mm vertical jump with a 530-gram payload. Beyond actuation, DEAs offer an enabling platform based on 3 pillars. These include self-sensing via capacitance changes, fluidics and haptics using DEA diaphragms, and programmable optics through internal electrodes for shape morphing. Working with DEAs requires high-voltage safety protocols. These include interlocked safety cabinets, insulated fixtures, fixed wiring to prevent handling energized leads, and current-limited HV supplies with automatic shutoff at breakdown thresholds. To achieve low-voltage viability and industrial integration, a multi-layer approach is critical. A 20-layer stack, compared to a single thick dielectric, achieves high lateral strain and displacement at 500 volts instead of 5,000 volts. The future of artificial muscles is defined by a coupled challenge: low-voltage operation, defect-tolerant fabrication, environmental reliability, and soft control systems. Dielectric elastomers are transitioning from a physical principle to an emerging engineering technology.